Hello friends, welcome to Susan and John MATHTUBE. This is lesson number 5 in exam preparation series. And in this lesson, we will continue our discussion in maxima and minima. And these videos are specially prepared for the first year engineering students who are studying in TU affiliated colleges. So, before we start, as always, I want you to read these things. And I hope you're using a pen and a paper while watching the videos. And I also hope you're able to work out the questions from your past paper questions. So let's start. Okay, and this is exactly where we stopped in the last video. We learned about function in one variable, and then we learned how to transform function in two variable plus one condition into one variable, and function is three variables plus two conditions into one variable. And then we learned this. So we have completed up to this. Now we are going to deal with functions in three variable and one condition. So the picture itself tells you there are two options. Option number 1, reduce it into a function in two variables and use the process we learned yesterday. And another method is converting it into Lagrange's method. So let's learn the Lagrange's method. So I want you to focus here. So we will be given a function in three variables plus one condition. And I'll repeat, you have two options. So let's start with Lagrange's method. So let f be the function and phi equal to 0 be the given condition. So you take all the quantities or the terms in the condition to the left side and call it phi. Yeah, I already told you, you don't have to do Lagrange's method. If you want, you can reduce it into a function in two variables. Okay, so the first thing you do is you form something called capital F. Capital F is actually small f plus lambda times phi. Then you find all the possible first order derivatives. That is fx, that means you differentiate with respect to x, y, z, and then lambda. Now using these equations, that is we equate all these quantities to 0 and we find the stationary point. Now to test, and this testing part will be a little bit difficult if you don't have calculators or if the determinants, actually delta 1 and delta 2 are two determinants, and if the determinants contain some non-numerical values. So there it goes. Here is our delta 1 and our delta 2, and if delta 1 greater than 0 and delta 2 less than 0, maximum point, and if both are less than 0, minimum point. You can take a screenshot or a print screen of this page. You have the formula here. So once more, we form the Lagrange's function and then equate all the first order partial derivatives to 0 and anyhow solve. And the testing, that's delta 1 and delta 2. I'll repeat, if the determinant contains non-numerical values, then it will be slightly difficult to expand delta 2. Anyway, this is the condition. So let's start. So obtain the maximum value. It's actually question number 2. Question number 1 is in video lesson 4. Yeah, so obtain the maximum value of the function x into y into z, so that x plus y plus z equal to 24. So clearly function in three variables plus one condition. And like I promised, you have two options, Anyway, I'm going for Lagrange's option. So let f equal to x into y into z. And for the condition, what I do is I take everything to the left side and I'll equate it to 0, and I'll call that quantity to be phi. And then I'll form the Lagrange's function, and here I have the Lagrange's function. I hope you remember the process. So we have the first order partial derivative with respect to x. When you differentiate with respect to x, y and z are treated as constants, so you end up with yz into 1 plus lambda into 1 plus 0 minus 0, and the same thing. And f lambda means lambda is the only variable, so this part will vanish and this will be a constant, so constant into 1. Anyway, now equate all these quantities to 0. And now you have to solve them. Anyhow solve them. So one method is you can find the lambda value from here. That's exactly what I did. Yz equal to minus lambda, zx equal to minus lambda, xy equal to minus lambda, and x plus y plus z equal to 24. And that actually implies these three quantities are equal, because all are equal to minus lambda. See, these three quantities are equal. Now take a look at the first two. If you solve this, to be honest, you have to take two possibilities, but I'll go for the second possibility. Yeah, I'll repeat. You can solve this, then this, and now you plug in all these values here. That is, instead of y you can put x, instead of z you can put x. That means x is equal to 8, but x is equal to y is equal to z, so the point is 8, 8, 8. Okay, that's it. Now the testing part. So before you start the testing part, that is before you find delta 1 and delta 2, be a little bit systematic, and you'll find it very easy to find delta 1 and delta 2. Second thing, be ready with a calculator which can solve fourth order determinant. Okay, so now look at this. Write it very neatly in a page. So phi x, phi y, phi z, that is, I'm differentiating with respect to x, y and z, and small fx. Yeah, one very important thing, capital F will never be used after you find the stationary point. Now second order derivatives. So I hope you still remember from the first few videos. So here I am differentiating x with respect to x, and that gives 0. Here I am differentiating y with respect to x, so that will give me z into 1. Okay, that's it. So I'll repeat once more. Make sure you do this neatly in a paper. Okay, now let's go for delta 1, and I have kept all the values on the right side of the screen. The question, then all the derivative values, and the point to be tested for maxima or minima. So this is the first determinant. It's very easy to write. You just write 0 and take a look at this. You collect the data from here. 1, 1, 1, 1, and then this much. And you can actually plug in these points. So it will be 0. What's the set value? 8. 8, 0. Now take a calculator and solve it. Okay, so we got 16, but 16 has nothing to do with the testing part. Is it positive or negative? Yeah, positive. Now for the big determinant, it's very easy. 0. Now you collect all these numbers. So 1, 1, 1, 1, 1, 1. And then you copy all these quantities at 8, 8, 8. So that will be 0, 8, 8, 8, 0, 8, 8, 8, 0. So don't waste time expanding this. If you want, you can expand, and the rule is same as for the third order determinants. So you write 0 into something that's gone, and then minus, you leave this row and this column, and you'll be able to see a third order determinant, plus 1, and then you just leave that row and column, you'll see another third order determinant, and finally minus. But using a calculator will be a very wise decision. So use a calculator and evaluate. So I got minus 192. That minus has a lot to do. 192 has nothing to do here. Negative. So I gave you the condition. That means delta 1 positive, delta 2 negative. That means this point corresponds to maximum. And this is our function. So plug in the value 8 into 8 into 8, and you'll get the maximum value. And once more, I'll remind you, if you want, you can reduce this function in 3 variables plus 1 condition into function in 2 variables. And you can use the procedure which we learned in lesson number 4. And that's method 2. So we have the function and the condition. So what I do is, I'll find the value of one variable and put it in the function. So here I am trying to eliminate z. So I found the value of z from this relation, and that's it. You can see a function in 2 variables. And now you can use the method which we learned in lesson number 4. Okay, let's move ahead to another problem. Find the minimum value of x square plus y square plus z square when x plus y plus z is equal to 3a. So I'll keep the question here. Okay, so look at this function in 3 variables and 1 condition. So like I told you before, you have 2 options. One is Lagrange's method, and another method is you find z from here or y from here or x from here and eliminate one variable in the given function and proceed with the method which we learned earlier. Anyway, I'm going to work out this problem with Lagrange's method. So let capital F equal to small f plus lambda into phi, and that gives me a function which looks like this. Now do you remember the procedure? Yeah, all the partial derivatives, fx, and it's not that hard to calculate, fy, fz, and f lambda. Remember, f lambda means you're differentiating partially with respect to lambda. That is, you assume lambda to be the only variable, and when lambda is the only variable, all these quantities will be constants. So when you differentiate, this will vanish. And for the second part, what happens is this part will act as a constant into the derivative of lambda with respect to lambda will be 1. Okay, I have the partial derivatives here. Now the solving part. So equate all the partial derivatives to 0 and use any technique which you like and solve. Anyway, here I'm going to equate everything to lambda, so I can see that 2x is equal to minus lambda, 2y is equal to minus lambda, and 2z is equal to minus lambda. But these lambdas are equal, that makes 2x equal to 2y equal to 2z. And that's it. I got x equal to y equal to z. Now I'll plug in this into the last condition. So x, the value of y is also x plus x minus 3a equal to 0. Yeah, so we got the required point. One advantage of Lagrange's method is you'll find it very easy to find the stationary point. But the disadvantage of Lagrange's method is the testing part. Finding delta 2 will be a little bit difficult without calculator. But if you have a calculator and if the determinant contains numbers, then this method is easier than the previous one. Now let's start testing. I told you before you find delta 1 and delta 2, make sure you do these things systematically. So here we go. We have phi x, that means the partial derivative of phi with respect to x, y and z, and then our fx, fy, fz, and the second derivative. I hope you still remember how we calculate these quantities. And then the second one, the last one. Okay, now let's go for delta 1. The good news is we don't have any variables here, so it's going to be very easy. So I hope you still remember how to write delta 1 in a very easy manner. Look at this. You write 0 as the first element. Then focus only on this much part. And then you put 1, 1, 1, 1, the values which I got here. And then 2, 0, 0, 2. And if you want to write the formula, you can write the formula. Use a calculator, evaluate it. Okay, this 4 has nothing to do, but this negative is important, so it's basically less than 0. Now delta 2, I told you the trick. First you put 0, then you write all these values 1, 1, 1, 1, 1, 1. Now copy this. So you're going to get 2, 0, 0, 0, 2, 0 and 0, 0, 2. Okay, that's it. And use the calculator, and that is negative. So both delta 1 and delta 2 came negative, and that implies our point is the minimum point. And don't forget our function is here, so we'll plug in this point and we'll find the minimum value. This is the minimum point, but we are asked the minimum value, and that will be a square plus a square plus a square. That gives me 3a square. Okay, that's it. Now let's move on to one more question. So find the minimum value of x square plus y square plus z square along with the condition ax plus by plus cz equal to p. Okay, the condition looks a little bit weird than the last two questions. So I'll put the question here, and like I told you before, you have two options. If you want, you can eliminate one variable from the function using the given condition and use maxima minima of two variables. Anyway, I'm going for Lagrange's method. So f equal to x square plus y square plus z square, and the condition ax plus by plus cz minus p. Now what I do is I'll form capital F and then the partial derivatives one by one. So that 2x plus 0 plus lambda into a into 1 plus 0 minus 0. So I hope you're okay with these things. And now what we do is we will equate all these quantities to 0. And that gave me 2x equal to minus a lambda, 2y equal to minus b lambda, and this, and the condition. And now look at this. From the first one, I can see that 2x by a is equal to minus lambda. Similarly, 2y by b is equal to minus lambda, and 2z by c is equal to minus lambda, and the lambda value should be equal, and that is how I got this. Now I will use the first and the last, and I will write x in terms of z. Then I will use the second and the last. So I'm going to write 2x by a is equal to 2z by c, and that gives me x is equal to a by c into z. And then I will use the second and the last, that means 2y by b equal to 2z by c, and once you simplify this you will get b by c into z, and I'll plug in these values in the condition. Now instead of x I can use this, and instead of y I can use the second condition. And now simplifying, you can take z common, and you will end up with a square by c plus b square by c plus c is equal to p. If you want to create a common denominator, you can do like this, and that will give me z equal to c p the whole divided by a square plus b square plus c square. Okay, now I will plug in this z value here. So I'll get x equal to a by c times c p by a square plus b square plus c square. So cancelling. Okay, so here we go, and finally this. I told you the condition itself was weird, so we are going to get something really complex. So the required point is ap by a square plus b square plus c square, and then the one with b, and finally the one with c. Now it is testing time. So before that, you do these things systematically. So the given function and the condition. Now the partial derivative with respect to x, y, z for the condition, and then for the function. And I'll repeat once more, capital F will never be used after you find the stationary point. We find delta 1 and delta 2 using small f and the given condition. So the second order partial derivatives, this is actually differentiating y with respect to x and z with respect to x. Okay, that's it. Delta 1 will be, yeah. So we have some non-numerical values, so you cannot use a calculator. So expand. I hope you still remember how to expand a determinant. So we get, okay, that's really nice. So tell me, is this negative or positive? Square quantities can never be negative. So the quantity inside the bracket is definitely positive. So we get, provided a or b is not equal to 0. And now for delta 2, again non-numerical values, so you cannot use your calculator. Plus minus, but the good news is the first determinant will be 0, so you will end up with, yeah, and expand. Okay, that's it. So negative. So look at this, delta 1 and delta 2, they are both negative, and that means the point which we found earlier is a minimum point. But look at the question, they didn't ask you the point, they want the value. That means you plug in this point in the function, and that will give us, yeah, there's something common. Now we can cancel, and that's it. Okay, so we did 3 very important questions for your exam, but from the past papers I collected a few more questions. That is, find the minimum value of this first question, the second one, the third one. And I want you to try these questions now itself. So take some paper and pen and start working out these problems. And if you're able to solve, then like, share and subscribe. And if you find the videos useful, do the same thing. So I'll be back with another video. I was planning to start multiple integrals, but I thought I will upload the video with 2 proofs from vectors, because I saw those proofs in many question papers. So I'll be back with another video very soon. So till then, bye.